National Aeronautics and Space Administration strives to reach for new heights and reveal the unknown to benefit all humankind. In this pursuit, we explore places never before seen by humans, reaching out into the vast unknown of space. While doing so, we learn more about ourselves in the process. Part of that mission is the responsibility of what is called planetary protection, both protecting our own precious home and protecting the undiscovered country that we are now pioneering from any harmful contamination we could introduce. Whether it's a rover landing on a distant rocky world, robotic probes skimming the surface of liquid-spewing moons, or returning samples back to our own home planet from a faraway celestial object, the Office of Planetary Protection strives to protect all of the planets, all of the time.
The importance of planetary protection is not just an issue of international treaty and legality. It's a simple scientific lesson we've learned from Earth history. We all know the hard environmental lessons learned from past mistakes of contamination here on Earth. From invasive flora and fauna tracked from one continent to another, from seagoing natives that become lakefront pestilence, from infestations of small vermin spreading predator-free across vast landscapes, we must remain vigilant to not expose our largely unexplored planetary neighbors to contamination. It's our responsibility, and greatly to our advantage, to prevent invasive species in interplanetary exploration as well as on Earth.
Obviously, rabbits and iguanas aren't the type of contaminants that could stow away on a robotic planetary mission. But is it possible to take microbial life accidentally to another world? What if we contaminate a planet with bacteria from Earth before we have a chance to determine if life exists there naturally first? All the science we would do there would become compromised forever, tainted or lost.
We know from science that life adapts to extreme environments in unexpected ways. Frigid polar caps, once thought barren, teem with tiny, enduring forms of life. Hot, scorching deserts are often homes to hibernating creatures that spring into life with the onset of rain. Take, for example, the Himalayan tardigrade or water bear. A mere 1/16 of an inch long, they can survive freezing in liquid nitrogen and boiling in water, and can stay dry and dormant for years. These little creatures have even survived biological experiments aboard spacecraft, living through exposure to the vacuum of space. Planetary protection is here to make sure we don't unknowingly take hitchhikers with us further into the galaxy.
When we explore new landing zones and places of interest, we want to confirm that native life isn't already there before we contaminate or displace it with Earth life riding aboard robotic explorers, or the eventual first visit from human explorers. We also need to know that the places astronauts will eventually set foot are safe for exploration. Therefore, NASA scientists and engineers are working hard at overcoming every obstacle that could get in the way of humans going to our next destination, with robotics, rockets, suits, and more. And planetary protection is part of that journey to Mars, in development, clean rooms, launches, and landings.
So what does the Office of Planetary Protection do? The first step is to identify how the mission will interact with the planetary target. Most objects in the solar system don't provide habitats for Earth life, so protection of these objects is easy. We just keep records of what our spacecraft do and where they end up. Today, there are only 3 solar system objects that are known to provide possible habitats for Earth life, so these objects have the most stringent restrictions. Each one is unique, studied in different ways and with different instruments. Flybys of Jupiter's icy moon Europa, with its subsurface global ocean, or of Enceladus, Saturn's tiny ice-ejecting moon, are much different from the exploration being done today on and around the planet Mars, with robotic orbiters and landers. From the Viking project's historic firsts in Mars exploration, to today's Curiosity rover and Mars Reconnaissance Orbiter, to the future Mars 2020 rover, these missions were carefully treated to avoid accidentally releasing Earth life.
Flyby, orbit, land, rove, or even sample return. With each future mission comes its own set of planetary protection guidelines and monitoring systems. After the mission is identified, the next step is to figure out how to keep Earth microbes away from the hardware that will interact with the target's surface. Clean it,
Wrap it,
Bake it,
Planetary Protection monitors NASA clean rooms, rooms that have specially designed, controlled environments where scientists and engineers prepare payloads and delivery systems for mission. The clean room bunny suit, as it's called, keeps human contaminants contained, making sure the clean room stays a clean room down to the microscopic level. From ground processing to launch, flight, landing, and beyond, Planetary Protection remains vigilant.
We have the responsibility to keep Mars and other planets pristine for scientific investigation without influence of Earth-borne contaminants. We want to know if there is life on other planets, and to find that out, the data must be unspoiled. For example, if your roommate sees your nice new contaminant-free carton of milk sitting in the cold environment of the refrigerator, do you want them to use a clean glass to get their milk sample? Or should they just drink directly from your carton and expose the rest of the milk, and eventually you, to their biological hitchhikers?
We also have the responsibility to make sure that future astronaut crews will be safe when observing the red planet in person, and protect planetary resources for possible future use. Most importantly, we have the responsibility to protect our planet Earth from exposure to possible alien microbial life that could be present in samples returned by robotic or crewed missions. The Office of Planetary Protection is here to protect all of the planets, all of the time.
All of the planets, all of the time.
All of the planets in our solar system, including the Earth.